Hey guys, welcome to 12.4a, Z-scores day 1. So a Z-score is a new way that we're going to be calculating standard deviations. It's a new way to measure data in a normal distribution, and you're going to kind of see how it works. Today is just the very basics for it. We're going to be doing a lot of simple calculations, and then the next lesson is going to be applying the Z-scores a little bit more. So just recall that some of the vocab that we use quite a bit, and we're going to continue to use. The mean is the average, or the sum of n numbers divided by n. It's always in the center of the bell curve, so that very middle point in our normal distribution. Then the standard deviation, that describes the typical difference or deviation between the mean and a data value. So the new thing that we're learning about is Z-score. This is how many standard deviations away we are from the mean. This can be a whole number, can be a decimal, can be a positive number, a negative, because we're going to be looking at positive and negative standard deviations away, just like what we did talking about the normal distribution. And then here's the formula. Z is equal to x minus mu divided by sigma. Remember that mu is the mean, so that's this part right here. And then this is sigma, and then the observed value, so whatever number we're looking at specifically from the data set, that's the observed number minus the mean divided by the standard deviation. And that's going to give us the Z-score, or the standard score. So the Z-score is how many standard deviations away we are from the mean. So if we look at some of the very first significant points, so if we have mu plus 1, like what we have here, that is one standard deviation to the right of the mean. Where if we have mu minus sigma, that is minus one standard deviations away, because it's to the left one standard deviation. And then here we have 2, and here we have negative 2, because this one is going to the right. So if it's a positive number, you know it's on the right side of the mean, and if it's a negative number, that means it's on the left side of the mean, because it's less than. All right, so let's go ahead and practice finding Z-scores. The first question says, what is the Z-score for a daily production of 2100, given that the mean of 2180 units and a standard deviation of 50 units? So this is already mapped out for us. 2180 is the middle, and then we would add 50 to the right numbers and then subtract 50 until we get to that third standard deviation. Now, 2100 doesn't fall exactly on one of these, and if it doesn't fall exactly on one of the numbers, like 2080, then it's not going to be a perfect number, it's going to be a decimal, which is completely fine. So we are going to get Z equals, X is the number we're observing, so that's 2100, minus the average, mu, is 2180, divided by the Z-score of 50. So what we end up getting, and this is important, note that we are subtracting a smaller number from a bigger number, so we get negative 80 divided by 50. And if you type that into your calculator, you're going to get negative 1.6. And negative 1.6 is the Z-score. So what that tells you is we are 1.6 standard deviations to the left. So that's another way you could write it. 1.6 standard deviations on the left of the mean. Now we're not going to interpret this like it every time. I'm just trying to explain what that means, but we are approximately 1.6 standard deviations away from the mean with that number of negative 1.6. All right, so now we're just going to practice finding standard deviations. It's going to give us a normally distributed set of data where the mean is 30 and the standard deviation is 5. So let's go ahead, let's actually build this graph. You're going to draw that. And we're just going to practice making the curve here. And then we make our middle point. 1, 2, 3. 1, 2, 3. Okay. So the mean is 30, and then the standard deviation is 5, so it's going to be 35, 40, 45, 25, 20, and 15. And then we could go ahead and just fill in our numbers here. It's not super important for this one because we're not looking for a percentage just yet, but we are going to be able to use the z-scores in the future to find these percentages. So that's the nice part about the z-scores. There's a purpose beyond these. All right, now 40 should be jumping out at you. Watch what happens when we use the formula of z equals x minus mu divided by sigma. So I'm just going to write that up here so we remember what that looks like. So the observed number that we're looking at is 40. So it's 40 minus the average, which is 30, divided by sigma is 5. So we get 10 divided by 5, which is 2. So the answer to this first part is 2. But notice, if we look at the mean, which is 30, we are 1, 2. 40 is a significant number because it's exactly 2 standard deviations above. So we actually could have predicted that the answer was going to be 2 without even using the formula. So if we think about part B, that's 25. So we go back 1, which means our answer is just going to end up being -1. And we could prove this. We could do 25 minus 30 divided by 5. You would end up getting -1 if you did it out by hand. But if it's a nice number that we know is on the graph that we can just determine right away, you can go ahead and jump to that part. Now 31 and 18, those are not nice numbers that we see. So those are for sure going to be decimal answers that we're going to need to do a little bit of work. So this is going to be z equals 31 minus 30 divided by 5. That ends up being 1 divided by 5, and that ends up being 0.2. We are 0.2 standard deviations. That's pretty close to the average. And then 18 minus 30 divided by 5 is going to be -12 divided by 5, which is -2.4. So that is 2.4 standard deviations to the left of the average. So these are pretty straightforward. Like I said, it's just a lot of simple calculations, understanding how to use the formula properly. Nothing too crazy just yet. So here's another set of data that we can go through really quick. Same situation, just a different graph setup. It's not my best graph, but it will do. 1, 2, 3. And then our average here is 81. Standard deviation is 6.3, so we're going to add that. We get 87.3. We get 93.6. And we get 99.9. And then going to the left, we're going to get 74.7, 68.4, and 62.1. All right, so now let's go ahead and let's calculate these. So this is going to be 65, or z equals 65 minus the average is 81. I'm going to write the formula up here again. And then sigma this time is 6.3. So we are going to get some decimals, but if you type this in your calculator, it's about -2.54 standard deviations if we just round that off. This one is going to be 83 minus 81 divided by 6.3, which is about 0.32. I'm just not going to go through the calculator part and make this any longer than it needs to be. Another thing, if you see this notation, so if it says z of 93, you might see that. What that means is 93 is the number you're observing, so it would be 93 minus 81 divided by 6.3. That comes out to be about 1.90, but we're just going to go 1.9. And then again, if you see this notation, it's saying 100 is the observed number. Divide that by 6.3, comes out to be 3.02. So that's pretty far above the average that's over 3 standard deviations above. All right, just a couple more here. We're almost done. So number 4, a class had an average score of 75 on Unit 10 tests with a standard deviation of 6. If Marco has a standard z-score of 1.25, what was his score for the test? So just really quick, I want to mark this part. So that's 75, and then sigma is going to be 6. So this time, we want to figure out what the test is based off of the z-score. So if we think about our formula, the parts that we know is the z-score, the outcome. So that's going to be 1.25. And what we're trying to solve for is the test score. So that's the observed number. So it's going to be x minus the average is 75 divided by 6. So we just have to solve backwards. So the easiest way to do this is multiply both sides by 6. So you would end up getting 7.5 equals, and then if we multiply by 6 on this side, so I'll do it like this, those 6's are going to go away, and we're going to have x minus 75. 7.5 equals x minus 75. We're going to add 75 to both sides, and we end up getting x equals 82.5. So this is the other cool part. You can figure out specific numbers given a standard or a z-score and knowing the average and the standard deviation. So another problem just like this, Emily had a standard z-score of negative 0.45. Would you expect her score to be above or below the average? With this one, the important piece to note is the negative, not the fact that it's a decimal, but it's negative. So that means it's to the left, so it's less than the average. So we would expect her score to be below average because of the negative. Now we can find it and prove this. So using negative, I'm going to do 0.45. That's the z-score. So we're filling in this equation over here. We're trying to solve for x, and we know that the average is 75 and the standard deviation is 6. So just like with the last one, we're going to multiply both sides by 6. 6's go away here. And what we're going to end up getting on the left side is negative 2.7 equals x minus 75. Add 75. And we're going to get x equals 72.3, which is below average because it's less than 75. And I guess I should put percentage on these. All right, one more to go here. Before applying to law school in the US, students need to take an exam called the LSAT, and before applying to medical school, students need to take an exam called the MCAT. Here are the summary statistics for each exam. So it gives you the average for both, and then it gives you the standard deviation. Notice this number is a lot larger, and also the standard deviation is larger, so we're going to see more of a spread in like the increments, whereas the MCAT is a much smaller number for the average, but relative to the size of the standard deviation, we actually would have a bigger disparity with the MCAT scores just because of how small the average is and how large the standard deviation is in comparison to that. Juan took both exams. He scores a 172 on the LSAT and a 37 on the MCAT. Which exam did he do relatively better on? Notice for both of these, we're above the average, so we know that we're going to have a positive standard deviation, so a positive z-score. Let's go ahead and calculate both, though, and then we can make that decision. So for the LSAT, our z-score is going to be 151 minus, I have that backwards, 172, because that's what we're observing, minus 151 divided by the standard deviation here is 10. So this is going to end up being approximately 2.1 after you do all of that. So that's at least 2 above. So that's a pretty good standard deviation, probably a pretty good score. The next one is the MCAT. So the z-score here is going to be 37 minus the average of 25.1 divided by 6.4. And that comes out to be 1.86. So since we're comparing the z-scores in terms of like standard deviation and how well this student would stand out, 2.1 is more significant than 1.86, so their LSAT is probably a better score. So we are going to say the LSAT for our answer.